So up until now, we've spent a ton of time in the V-engine talking about data, right? We've got our entities and our components, but let's be honest, data by itself is pretty boring. It's static. It doesn't actually do anything. The real magic, the thing that makes a game engine feel alive, is when we add behavior, when we turn all that static data into a dynamic, interactive world. Today, we're diving deep into how that magic happens, the behavior layer, all powered by systems. So here's our roadmap. We're going to start with the basics. What exactly is a system? Then we'll look at their life cycle, how the engine manages to orchestrate all of them frame by frame, and the different ways they can communicate. We'll even get into some really cool, advanced stuff for coordinating complex work before we wrap it all up. Sound good? Let's jump in.
Okay, so this is the core problem we need to solve. We have our entities, which are just unique IDs, and we have components, which are basically just bags of data. So how do we take an entity that has, say, a rigid body component and actually make it fall with gravity? How does any of this data actually spring to life?
Well, the answer is the systems. And this table honestly lays out the beauty of the ECS architecture perfectly. Entities, they're just for identity. Components, they're just for state. All of the actual logic, all the behavior, lives inside of systems and only inside systems. So a physics system is going to look for every entity with a transform and a rigid body and, apply physics to it. An AI system finds all the entities with AI components and tells them how to act. The data is totally passive. The system is the active engine of change.
Right, so we need systems, lots of them. A modern game engine is going to have dozens. Rendering, physics, audio, AI, you name it. And that brings us to our next big challenge. How on earth do you manage all of them? How do you make sure they all get initialized and cleaned up properly? And how can you access them from anywhere in the codebase without creating a complete tangled mess?
The solution starts with a simple but really powerful idea, a contract. In the V-engine, every single system has to follow the same predictable lifecycle. We call it a base system. It's got three key methods: init for any one-time setup you need to do, update DT for all the logic that runs every single frame, and shutdown for when it's time to clean up. Simple, right? But it's incredibly effective because every system plays by the same rules.
But what about accessing them? Well, that's the other half of this elegant solution, the Singleton pattern. By having our systems inherit from both the base system and a Singleton template, we get the best of both worlds. We get that unified lifecycle, and we get safe global access. So now, any other part of the engine can just call renderSystem.instance and get a pointer to the one and only render system. No messy dependency injection required.
And what this gives you is just incredible stability. It's a guarantee. As a developer, you know for a fact that init will be called exactly once before any updates ever happen, and you know shutdown will be called exactly once at the very end. That kind of predictability is what you build a robust, stable engine on.
So, our systems all have a predictable lifecycle. Awesome. But now, a new problem emerges, and it is a big one: order. In what sequence should all these systems run every frame? I mean, it's absolutely critical that you process player input before you run the gameplay logic, right? And you have to run your physics simulation before you render the results. If you get that order wrong, you get chaos, you get weird bugs, and you get that frustrating one-frame input lag that drives players crazy.
The engine solution here is a system manager that uses priority levels. The best way to think of it is like an orchestra's conductor. The conductor doesn't actually play an instrument, right? They just tell everyone when to play. It's the same idea here. Critical systems, like loading configs, go first, then high-priority stuff like input, then the main show, rendering and physics, at a normal priority. And finally, low-priority systems like AI run at the end. This creates a stable, deterministic update loop every single frame.
And here's what that actually looks like in the code. It's super straightforward. When the engine is starting up, it just registers each system with the manager and gives it a priority. So the input system naturally gets added with high priority. This guarantees it runs early in the frame so it can capture what the player is doing the instant it happens.
And in contrast, you've got something like the AI system. It gets registered with low priority. And that makes perfect sense, because the AI's decisions probably depend on where the player moved and what the physics did, so it runs later in the frame. The system manager just collects all of these, sorts them once, and then it has a perfectly ordered execution list ready to go for the entire game.
Okay, our systems are running, they're in the correct order, but they're still kind of in their own little bubbles. How do they actually talk to each other? When the physics system detects a collision, how does it tell the audio system to play a bang?
or the UI system to update a health bar, or the gameplay system to actually apply damage. That's the next big piece of this puzzle: communication.
In the V-engine, you basically have 3 main tools in your toolbox for this, and knowing which one to pick is super important. If you have systems that are really tightly related and need an answer right away, you use a direct reference. If you just want to shout out a notification and not care who's listening, that's loose coupling, and that's a job for the event system. And for really heavy, expensive work that you can run in parallel, you hand that off to the job system.
Let's focus on those first 2. It really all comes down to a trade-off in latency. A direct reference is like making a phone call. You need an answer now, and you're going to wait on the line until you get it. But the event system is more like sending a text message. You just fire it and forget. You move on with your life, confident that someone will handle it later. This deferred approach is fantastic for decoupling things. When a player dies, the combat system can just send out a player died event, and the UI, audio, and AI systems can all react to it without the combat system even knowing they exist.
All right, now for the real powerhouse in our communication toolbox, the job system. This is how we handle really complex parallel workflows that just don't fit into that simple, linear update loop of the mainframe.
And that really brings us to the key question, right? That System Manager priority list is great for ordering whole systems, frame by frame, but what about the little tasks inside a single system? I mean, think about the render system. It has a ton of different steps. Some of those steps absolutely have to happen in a specific order, but other parts could totally run in parallel to save time.
And this slide nails the essential difference between our 2 schedulers. The System Manager priority is static and broad. It sets the order for entire systems for the game's entire lifetime. The job system, on the other hand, is dynamic and incredibly precise. It lets you define dependencies between individual jobs, giving you fine-grained, task-by-task control inside of a single frame.
Think of it like a render pipeline. It's the perfect analogy. Before you can render shadows, you first have to calculate all the lighting in the scene, right? So the shadow rendering task has to wait until the lighting task is done. And then you can only apply your post-processing effects after the shadows are finished. The job system lets us build this exact chain of dependencies, guaranteeing this precise order of operations every time.
And what's so cool is how you actually write this in code. You're not guessing. You are explicitly declaring the dependency. When you go to schedule that shadow job, you literally tell the system, hey, run this, but only after job lighting job is complete. It's a declarative style that makes even the most complex workflows really clear and safe to manage. And it goes way beyond just simple dependencies. The job system is incredibly flexible. You can schedule a job to run after a specific time delay. You can tell it to run only every 2 or 3 frames to spread out the performance cost. You can even tell it to run only when the CPU is idle, which is absolutely perfect for background tasks like loading and streaming assets.
All right, that was a lot to cover. Let's take a quick breath and see how all these different ideas come together to form one cohesive, high-performance architecture.
So let's recap the journey. We started with a core rule. All behavior lives in systems. We gave them a predictable lifecycle and easy global access using that BaseSystem and Singleton combo. Then we brought in the System Manager to act as our conductor, creating a stable, ordered frame. We looked at how to choose the right communication pattern, balancing immediate needs against the flexibility of just firing off notifications. And finally, we unlocked super fine-grained control over our parallel tasks with the job system's powerful dependency graphs.
You know, we've explored all these powerful ways systems can be organized and scheduled to run. But when they do talk to each other, a message is only as good as its content. So that raises a really interesting question. How do you design the perfect message? How do you make sure it gets delivered efficiently and only to the people who need to hear it? Well, that is exactly what we're going to tackle next time as we do a deep dive into the architecture of V-Engine's main communication backbone, the event system. I'll see you then.